Welcome to Recovering Evangelicals, a podcast for people who were once very comfortable in the Christian faith until the 21st century intruded and made it very hard to keep on believing. I'm your host, Luke Jansen.
And I'm Scott Dyer.
This is the third episode in a mini-series we've been doing on the topic of fine-tuning of the universe. Our first episode gave our listeners some background information that will help them when we bring on our guest experts. People who have PhD degrees in the relevant areas and are very passionate about this particular topic, so they might have a tendency to get ahead of us on the journey through the conversation. We'd recommend you go back and listen to that episode, number 164, if you haven't already heard it, before you continue with today's episode. In that introductory episode, we clarified that the term fine-tuning can mean three very different things. Last week, we heard from Ellie Fetter and Aaron Zimmer, who spoke about the first of those three meanings. The fine-tuning needs to produce a universe full of usable or interesting stuff, things like atoms and planets and stars. As shocking as it might sound, it turns out that even just to get just that, atoms, planets, and stars, requires razor-edge precision with respect to the fundamental constants and laws. The second and third meanings of this phrase, fine-tuning, have to do with what it takes to have life, a living universe. Either the fine-tuning to make it possible to produce any kind of life at all, which is today's topic, or the fine-tuning that people think is necessary to sustain the kind of life we have on Earth. We explained in episode number 164 why we think that third meaning of the phrase fine-tuning is, if not misunderstood, then at the very least it's really stretching the definition of fine-tuning. But back to the second definition of the phrase, the fine-tuning needs to actually produce life of any kind, anywhere in the universe. You see, it isn't just enough to produce a universe full of atoms and planets and stars. Life requires complex atoms. The main thing that stars like our own sun make is helium. Those stars, like our sun, have a lot of hydrogen, which is just a proton and an electron, and they smash two of these together to produce helium. An atom that's, well, obviously, it's twice as heavy as hydrogen. You take two hydrogens and smash them together to get a helium atom that's twice as heavy. This is what they call nuclear fusion. And it's possible to have a universe with stars and planets comprised almost exclusively of hydrogen and helium alone. But it's possible to also smash one hydrogen and one helium together to produce an atom that's 3 times as heavy as hydrogen, lithium. Or smash two heliums together to produce one that's 4 times as heavy as hydrogen, an atom called beryllium. Or a lithium atom and a helium atom together to produce one that's 5 times as heavy as hydrogen, aka boron. Or, well, okay, I think you get the idea. And again, it's possible to have universes with stars and planets composed only of these 5 elements: hydrogen, helium, beryllium, lithium, boron. That sequence of atom making from lighter to heavier atoms gives us what you might remember from high school, the periodic table. And the point of fine-tuning is that you need a certain degree of precision to create a universe that's full of hydrogen and helium atoms, but a completely higher level of precision, much finer fine-tuning, to get a diverse array of types of atoms. We've got 118 of these different types of atoms here on Earth, almost 90 of them occurring naturally, and the rest made in university laboratories. Some of the atoms on the light end of that periodic table, like carbon, oxygen, and nitrogen, which are numbers 6, 7, and 8 on that periodic table, these are needed to make the amino acids and proteins that all cells are made of. Some of the atoms, a little bit higher on the periodic table, like sodium, potassium, and calcium, numbers 11, 19, and 20 on the table, are needed to do a lot of very simple cell physiology, things like generate electrical signals and cause contraction. And some of the much heavier atoms, which are not only heavier, but also more complicated in their atomic structure, these are absolutely essential to the enzymes that keep us alive. Just think iron, number 26 on the table, and how your blood needs iron in order to carry oxygen. Or copper and zinc, numbers 29 and 30, or selenium, number 34, and molybdenum, number 42, in many of your liver enzymes. If you don't believe me, just check your vitamin supplements. You'll find these and others listed there. Without these atoms, these elements, in relatively high amounts, it just doesn't look like life could even be possible in a universe that has planets and stars, but not these heavier elements. This is what our guest expert will be referring to when he talks about the fine-tuning needed not just to produce a universe, but a universe capable of producing life, especially complex, intelligent life. To do that, we have Dr. Luke Barnes, who has a PhD in astronomy from Cambridge University and is currently a senior lecturer in astronomy and cosmology at Western Sydney University in New South Wales, Australia. He's published scientific papers in the field of galaxy formation and on the fine-tuning of the universe for life. So, as I often say on this podcast, he's the perfect guest to speak on this topic. Dr. Barnes, welcome to the podcast.
Thanks for having me on.
Yes, welcome. I've been reading your book that you co-authored and really enjoying it. And I appreciate, I know analogies always break down, but you come up with some really good analogies and illustrations that really help a guy like me. And I'm sure hopefully others understand these very challenging concepts.
Yeah, it's hard to draw that line between, can I try and just explain things the way they are? Or do I want to go for an analogy? And sometimes analogies turn out worse than the than the explanation they're trying to explain in the first place. But
yeah,
it's you do try and sit down and really think, okay, does this actually work? You try it out on a few people and see whether they glaze over. And
yeah. It's almost mean in a certain sense the idea of a priesthood, that there's these people with this elite knowledge that understand the mysteries of the universe, and none of us can really understand them. We'll just have to kind of trust that they know what they're talking about. Like I know when they built the Large Hadron Collider, there was actually apparently some concern that they could create a black hole, for example. And I thought, wow, we really putting a lot of trust in these guys.
Well, I feel a bit like maybe this is another analogy, but if I'm sort of somewhat interested in the history of science, and you sort of read, especially that sort of prehistory before what we call the scientific revolution, and even then, and at some point I come up against the fact that I can't read Latin. And I feel like it's that sort of like there's a language barrier, and I feel like maths is the language barrier for physics. And at some point you just sort of go, okay, what does this Latin, what does this really mean in Latin?
Right.
With the black hole thing, that's an interesting one because we were doing things in the end that wasn't a major problem, because the kind of thing that happened in that particle physics collider in Switzerland is the sort of thing that happens on the edge of our atmosphere every day.
Oh, okay.
So, it's a very simple thing in the end. You slam two particles together really, really fast.
Right.
Well, there's really fast particles in the universe, and they slam into the top of our atmosphere all the time with similar sorts of energies. Now, a Hadron Collider would do it in a denser environment where there's an instrument around it to see what would happen. But fundamentally, things have hit that hard in the universe before we did it.
Okay.
The interesting thing will be if we start reaching experiments that do things faster than the universe does them. But I think we're a way off that sort of limit anytime soon.
Just as a quick aside, is that the only way they can really determine what is a fundamental particle? In other words, what can't be split into something else by smashing particles together? Is that pretty much the way that we know an electron can't be reduced to anything else, kind of thing?
Yeah, more or less, because if you don't smash things fast enough, then a composite particle will look like a point particle.
Right.
Something made up of pieces.
Yeah.
Right. If you just sort of, glance a particle off the side, it'll look like it's a point. You won't be able to tell the difference between one or another. But the harder you smash it, the more chance you have of opening up what's inside, so to speak.
But they were able to predict some of these things even before they smashed them, right? Just through the math and stuff like that.
Yeah, it's quite an interesting and sort of complicated story that there were good reasons to think that there was another particle out there that we hadn't seen yet, this Higgs boson that they famously found. There were sort of good reasons to think that was doing things in the universe, and we saw the indirect evidence of that, but not the direct evidence of it. So, yeah, to finally put that extra piece in was very a major moment in the history of science.
Yeah. Okay. So talk about how you came to be a scientist and your religious context growing up and so on.
So I grew up in country New South Wales, out in the sort of middle of nowhere, near the beach, which was great, and grew up in a religious household, in a fairly academic sort of household. My grandfather was a scientist, a science lecturer in chemistry, so he was very happy that someone in the family was getting into these things. So with that, and then, growing up in that sort of household, I was good at maths, and then did physics near the end of high school and sort of had fun doing that. That was, if you can speak the language, then it's great fun. And so eventually ended up doing a physics degree and Did a research project as part of the final year of my physics degree and loved that. So I was encouraged to then sort of go apply for PhD positions because, you'll enjoy it because it's just more of the same. So I was lucky enough to get a scholarship to go to Cambridge and did my PhD there.
Was Stephen Hawking there at the time?
He was there at the time. So I will, at Cambridge, there's actually 3 different departments that do astronomy. Well, there was at the time. 2 of them are sort of amalgamated now. So there was physics, there was an Institute of Astronomy, and then there was applied maths. So I was in astronomy, and Hawking was in applied maths, applied maths and theoretical physics. But we would all get together for cosmology lunch on Monday. All the cosmologists across all 3 of those would get together. So he would turn up to those and listen and occasionally ask a question. So yeah,
that must have been quite an opportunity.
Yeah, it was. Yeah, I mean, he when he goes in the room, he's sort of, yeah, pretty cool, man.
Yeah.
So you mentioned you grew up in a religious home, but you didn't define that. Are you willing to do so or not?
Oh, sure. So I grew up Presbyterian. Yeah, my dad was a pastor. Still was until sort of he retired about a year ago. So yeah, grew up pastor's kid. Grew up in a young Earth creationist church. And that was sort of there wasn't a major sort of crisis of faith, but there was a crisis of how do I understand Genesis? I'm not that way inclined anymore. Yeah, it's a bit tough to be a practicing cosmologist. I think that 1,000 years old.
But wouldn't they say that God created the universe to look like it's billions of years old?
Yeah, so that's an option. It's funny for me, actually, one of the main voices in young Earth creationism today from a astronomy background is Jason Lisle, who rejects that particular hypothesis. It just makes the universe look. It means the night sky is effectively a painting. It's not,
right.
So here's the stars out there, but then whether they're there or not, God put them too far away for the light that they actually produce to ever get to Earth. And so God had to sort of paint around Earth here, this little 6,000-year light sphere. God painted the night sky in photons.
Yes.
He could, but it's a weird picture of, and then so you have this little sphere of the way God painted the night sky, which is not created by the actual stars out there. That's a very weird picture. So I find young Earth creationists who reject that and think there's other answers to the way that the science works.
Okay.
The way it sort of worked for me was as I started doing physics, I actually there was a sort of local young Earth creationist offices somewhere in Sydney. I sort of found them and I said, what have you got? And someone who has my eternal gratitude photocopied a whole bunch of articles about what's wrong with the Big Bang and what's wrong with modern cosmology. And it slightly backfired because as I went through my own education, I could then evaluate those articles, not as here's what they say, but here's what's, can actually evaluate the science there. And they all kind of fell apart. So that was part of my journey out of young Earth creationism. But there was no major crisis of faith as a part of that as well. I mean, if there turns out to be a book of the Bible I don't understand as well as I thought I did, then,
right.
that's not surprising. I still don't know what Revelation's about.
Okay. You've written many papers and you've co-authored this book that we referred to earlier. You talk about a universe that's finely tuned, but not just to come into existence, but to produce, and I use this technical term, usable stuff, like atoms and planets and stars, but also finely tuned to produce life as we understand it, including intelligent life. We spoke to Ellie Feder and Aaron Zimmer.
Yes. They sent me a sort of the scripts of the podcast series they did and then the podcast episodes, and I had to read, and then I was starting to write out some stuff, and then we had a Zoom chat with them, and they presented it this way, I've presented it that way. How does that work for you guys? It was very interesting. I think they've done a very good job of summarizing what the science is and what moves you could make philosophically with it.
Okay. So then our conversation with Aaron and Ellie last week concentrated on the first of those 2 fine-tuning questions, the fundamental constants which determine the appearance of the universe itself. And we really avoided the question of fine-tuning to produce life. Today, we want to do the opposite. We want to look at fine-tuning of the universe with an emphasis on it being fine-tuned to produce living organisms, even intelligent organisms. So give us your perspective on that, on why you claim the universe is fine-tuned for life.
So as a physicist, fine-tuned is part of my sort of technical toolkit. What it means in general is that something along the lines of you've had to make a suspiciously precise assumption in order for your model, your picture, your hypothesis about the universe to fit the data. So again, here's an example from the book. Suppose that you're a detective and you're called to a crime scene. There's been a robbery at a bank, and you pull the security tapes and you press play, and you see the robber comes in through the front door, walks up to the safe of the bank, and hits 16 digits on the number pad. Hits go, and the safe opens for them. Right? They knew the code. Takes all the money and goes. Okay, what hypothesis would we talk through about that? Well, the obvious one is someone told the robber what the code was. It's an inside job, right? And a pretty badly staged one. Suppose someone comes up with an alternative hypothesis that maybe the burglar put in their favorite number. They've got a favorite 16-digit number, and they went with that one, and that opened the safe. Well, the problem with that, and it's a little bit of a stretch to stick it into the fine-tuning mold, but you'd say, in order for that hypothesis to explain the data, you need to make an assumption that the code for the safe is equal to the burglar's favorite number. And it's suspiciously precise because there's a lot of 16-digit numbers, and only one of them, we assume, opens the safe. And if you don't have exactly that, then you don't open the safe. More generally, it doesn't have to be, it has to be exactly this. But if you have some idea about how the universe works, that will consist of a series of statements about the universe, right? It's made of quarks and they have this charge or these electrons or whatever. There's properties you need to associate with them that will take the form of just numbers, parameters. If those have to be suspiciously precise in order to explain the data, you have a case of fine-tuning. Now, it doesn't mean your idea is wrong. It just means that there's a scope for a better idea to come along and explain it better and win the day. So it's not that it's impossible that the robber just guessed the code or that the robber used their favorite number. It's just that there's a better hypothesis that we can glimpse, which is there in the off to the side. So it's suspicious. It's not conclusive. But so what we mean by fine tuning for life is, okay, well, there's the standard model of particle physics, the way the stuff we're made out of, electrons and all that stuff. There's a standard model of cosmology, the way the universe is set up as a whole. As part of that, there are numbers that you just have to put into those. These are the constants of nature. Right?
Can you mention a couple just to give us some context?
So, for example, how heavy is an electron? So if you remember your picture of atoms, there's the bit in the middle and there's the bit going around the outside. The thing going around the outside is the electron. How heavy is it? And there's a number there. There's the mass of the electron. And in kilograms, it's some extremely small number, but we know what that number is. That's an example of a fundamental constant. It's not that we'll never know why it is the way it is or anything like that. It's just today, in the best theory we have today, it's a number that we have to put into the equation. It's not a number that comes out of the equations. It's not a prediction. It's just a parameter we've got to put in. There's more of these. There's about 31 in total of numbers you just have to put in. And once you put them in, the theory does a pretty good job of explaining a whole bunch of data. Fine-tuning for life is then, all right, let's look at the sort of possibilities across all these different combinations of numbers. And what we find is that small changes for some of these constants, not all of them, but for some of them, I'd say a core group of maybe 10, what look like fairly small changes, or put it more generally, the sort of region of this higher dimensional space, the fairly small changes in those numbers do drastic things to the way the universe would turn out. They make it in most cases, much more simple, much too simple, in that, you don't get chemistry, which is great and lovely and simple, but just because nothing will stick to anything else. So if you have a picture of life that it needs at least some sort of complexity from the matter it's made out of, then you have fine-tuning for life. That if you looked at all those possibilities and isolated the set that would allow for any sort of conceivable form of life, then that's a very small subset of the total.
But one of the questions that I have then, when people talk about fine tuning for life, is though I'm getting at the idea that life can be very resilient, very versatile. Life can do some amazing things. We need to understand that we're talking about life as we know it right now, and we only know the kind of life that's formed on Earth, and that's because it's the only planet we've ever been able to do experiments on. So we understand how life on Earth works. And then we can try to extrapolate that to other forms of life which are nearly the same. So things, for example, life forms that are based on silicon instead of carbon, or life forms that extract electrons from molecules other than oxygen, or use reducing agents other than methane or ammonia. And some of the listeners will know the phrase Leo the lion says grr. Then you would know what we're talking about here. But we have no idea of what's possible when it comes to the producing something that we call living. It may be possible that there are forms of life that have completely different ways of doing things. And one example that I use, just to put it out there, they might not even have physical bodies, and they might be based on magnetism. So what do we do with the fact that we don't know exactly what life is? How the different forms that life can take?
I think I want to push back against the idea that we take life as we know it and sort of extrapolate outwards. For the most solid cases of fine tuning, we ask for very, very general conditions. So, for example, from cosmology, just another example of a constant of nature, there's something called the cosmological constant. All right, again, it's a number. What it represents in the model is this tendency, for reasons we don't fully understand, that there is something about the nature of space and time in our universe, we think, which all the contents of space and time in our universe, that makes the expansion of space accelerate. For some reason, in the universe today, there's a galaxy over there. We've known since the 1920s that it's probably moving away from us. What we've known since the late 90s is it's moving faster today than it was yesterday. So it's accelerating away from us. The number that sort of captures that effect is called the cosmological constant. What if it had been different? And over the full range of what the constant could have been, outside of a very small subset of that, the universe expands so fast that no structure is able to form. Right? In other words, no particle ever touches another particle. Right? So whatever you've made the universe out of, all you ever make is one of those things drifting in empty space on its own. And that's your universe. Now, under those conditions, if that's a case of fine tuning, what about silicon-based life? Well, you haven't made any atoms. What about methane? What about, people like to say, there's these tardigrades and they can exist at 120 degrees Celsius. I'm like, well, that's great. I made a universe where no particle ever touches another particle. What form of life do you think will form there? Similarly, if you change we talked about the mass of the electron, there's also the mass of the other fundamental pieces, right? Up quarks and down quarks, for the record. In that space, for almost all of the space of possibilities of those masses, again, no structure can form. You can't form a bonded thing. It's like a Lego set where just none of the pieces actually stick to each other, right? All you can make with that is a pile. So yes, around the edges of, if we had the whole sort of set of possibilities here, and we want to know exactly where life was, there would be some fuzziness around the edges where we'd have to work out, okay, silicon-based life, and what about methane and ethane and methanol and other ways that there could be solvents, and yeah, they'll fuzz the edges up a bit. But what I can do, and what we really do in life, because it's actually quite hard to predict a lot of these things, is put a very safe box around the outside of this region and say, outside of here, there's no periodic table, nothing touches anything else. Magnetic fields are caused by flowing currents. Well, there's no neutral, every particle in the universe is neutral. It's easy to make those universes, so there's no magnetic field, so that won't work either. Like I can just make very safe conditions and then say if the universe still turns out to be fine-tuned for life, even in those circumstances, then we can be pretty sure it'd be even more fine-tuned if I went into the detail.
Okay. So I'll reiterate what you said just to confirm that I understand what you're saying. You're talking about fine tuning of the universe to produce life involves whatever it takes to produce the various atoms, all the way from hydrogen all the way up to oxygen, carbon, nitrogen, iron, that sort of thing. That's what you're referring to.
Yeah, so when we do fine tuning, it's actually quite hard to do a lot of these predictions. The reason we think fine tuning is a real thing is because in a lot of these universes, the physics gets way, way simpler than it is in our universe. If all these other universes were like our universe, we'd struggle to know what would happen there, because it's very hard to take the bottom level of physics, the standard model, quarks and electrons and stuff, and say, okay, what chemical elements would form and what compounds are possible. Actually, getting even up to chemistry is very difficult computationally. But there are these very general arguments down here. Once you've simplified things a lot, because these numbers are different, that actually, well, there's no, we don't, if a bond can happen, then it's an open question of which bonds happen and how they arrange themselves and all that sort of stuff. If no bonds can happen because the energetics are just wrong, then now it's real simple, right? Nothing's going to happen, right?
Right.
Right. If I give you this, here's a Lego set and a 5-year-old kid and all the bits stick to the other bits, what are they going to make? Well, that's hard to predict. If none of the pieces stick to any of the other pieces, what are they going to make? Well, they're probably going to walk off into the other room. I mean, it's just easier to predict when it's so simple.
Right. And that reminds me now, when you mentioned that just a moment ago, you said about the bonds weren't just quite right. That reminds me of this story, which I'm not totally clear on. Fred Hoyle, a very distinct atheist, he's noted for saying some provocative things about it looks like the universe was monkeyed around, that some intellect adjusted the dials to produce, it has to do with the atomic structure of carbon and oxygen. And I know you know a lot more about this than I do. So what's the story there?
So it has to do with the nuclear structure of carbon. So here's my best attempt to explain this. The way that our universe makes heavy elements is by taking lighter elements and smashing them together hard enough and fast enough and hot enough that they fuse together to make heavier elements. This happens in the cores of stars. So our sun is doing this right now. It's turning hydrogen into helium. Right, so it's the first element in the periodic table into the second element in the periodic table. Once the stars run out of fuel, a couple of different things can happen depending on its size. If it's small, it will just run out of fuel and slowly cool off and become what's called white dwarf, and that's sort of the end of its life. If it's big enough, you can smash bigger things together to make even bigger elements in the periodic table. The way that works in our universe, there's a little bit of a problem. You smash hydrogen together to make helium, so the first thing becomes the second thing. The next obvious thing would be to smash 2 helium nuclei together. That would make beryllium, the fourth thing in the periodic table, the fourth element. The problem with that is beryllium is not stable. Beryllium-8 is not stable. If you just smash those two together, it falls apart before anything else happens. That's a real problem. A Lego set where you can put 2 things together, but you try to add a third thing and the whole thing falls apart.
Okay.
The way our universe gets around this is that there's what's called a resonance level, which is something I can, it's quite hard to explain exactly what's going on. Basically, as it's falling apart, there's a way that it can sort of wobble around for a little bit and be a little bit longer lived than we thought it would be and then fall apart. If that resonance level is there's enough time in a very hot and dense star for another helium to come along and a 3-body interaction happens. And you jump to the 6th thing in the periodic table, which is carbon. So the carbon in our universe is made by this process called the triple alpha process. It relies on that fact that this unstable thing actually takes a little bit longer to fall apart than we thought it would. So Hoyle actually predicted that resonance. He predicted a nuclear property of the carbon and beryllium nuclei based on the fact that there's carbon in the universe and it must have come about in stars. But if that wobble's not there, then no star ever gets hot enough for the triple alpha process to happen and no carbon ever gets made. And so he says, I think the quote is something along the lines of, a straightforward interpretation of the facts suggests that a super intellect has monkeyed with physics. If this rather special property wasn't there, well, let me be precise. every nucleus has, it'll vibrate and wobble in some way. The important thing is exactly the energy of that vibration. And if you get it at the right point, then as the two helium come together, that's enough energy to make that particular wobble, makes it stick around for a bit longer, and then along comes the third thing, and you're all okay. It's the fact that that energy level's at just the right place for all of this thing to work.
And why would he word it that way? He's a staunch atheist. As I understand it, he was against the Big Bang Theory at the beginning when it was first proposed, just because it sounded too much like what creationists might want to have happen, that the universe had a starting point. So he's a staunch atheist. Why would he use wording that says, talks about an intellect monkeying with the physics? Why would he do that?
I wonder whether, I mean, he eventually came around to some strange views about the origin of life. Directed panspermia. That basically there's no way life happened here on Earth, right? It's too unlikely. You can't. The origin of life, he thought, had to happen somewhere else, and so I wonder whether his super intellect wasn't God. It's life that's formed somewhere else by some other means and got much simpler. No, I don't know, something like that. Or whether there's something else going on there. So it's an offhand comment he makes, and he doesn't really follow it up. So it's hard to know exactly what he was thinking.
And if it was that, he's a very smart guy. He would, I'm assuming, he would recognize that just moves the goalposts. The super intellect, he says, is, I don't know, maybe I'm taking too much time on this point, but.
Well, even as far as the panspermia thing, I believe even Richard Dawkins gives a little bit of credence. Like he says that there's at least a decent possibility that life came from somewhere else, right? Because, like you said, the likelihood of it arising on Earth doesn't seem great. So, but yeah, it just pushes it back one. So how did that life come?
Yeah.
But can I ask a question though, Doctor? This wobble you're talking about, this resonance you're talking about, does that resonance exist because of one of these constants? In other words, if we didn't have the fine tuning we had, would that wobble not exist?
Yeah, so the later work by some particle physicists looked at how would that level change as I changed fundamental constants, the mass of the quarks. And they found that if you want a life-permitting universe, you've basically got an open window of about a couple of percent, maybe 2.5, 3%, to change the relative to its own value. And the quark values are already extremely small. So relative to the total range of possibilities, that's very finely tuned. And this is sort of where you do need to ask the right question in these investigations. Fred Adams, currently an astronomer at University of Michigan, looked into these cases in a lot of detail, done a lot of very good work in simulating what would happen. He points out that there's another way you could get around this problem, as well as you put the resonance in just the right place and then you're all right. You could try to alter the constants to make beryllium-8 stable in the first place, so you wouldn't have this problem when you start. That opens up more of parameter space to make for carbon-based life forms. There's a few open questions for me there. I think there's still a fine-tuning case, and it's interesting that our universe chose the fine-tuned level way of doing it rather than perhaps tuning it in other ways to get beryllium stable. But you've got to be sort of careful about the way that you sort of put these cases together, which is why I tend to rely on the much more general, much more broad cases of, can anything stick to anything else?
Right.
Yeah.
So what about, is it possible that in this fine-tuned universe we find ourselves, that even though it is fine-tuned at that kind of big cosmological level, that life still may not have arisen?
Yes. Yeah. So
okay.
The big sort of open question here is, how did life form in the first place? Which we don't really know. Certainly I don't. Someone out there might.
Yeah.
I mean, it's an extremely difficult problem. So I can't really blame people who work in this area for not having worked it out.
Yeah.
In particular, what we don't know is whether we're looking for a common process or a rare process. So there's an analogy here actually with how planets form. So if you actually read Hoyle's books from the 50s about science, there's the best idea they had about how planets might form is maybe every now and then there's just the buzz of stars around the galaxy. If two of them get close, one of them might rip a bit off the other one, and that material will form a disk and form planets, and that's how you form planets. Well, we know sort of how many stars are out there, how big they are, how much they're sort of buzzing around. That star-on-star process is extremely rare, and so if that's the way planets form, we're probably the only planetary system in our galaxy. Like, it doesn't happen very often. So then astronomy in the 90s goes, like 1995, we discovered the first extrasolar planet, and we've found planets around all sorts of other stars. What that tells you is that that star-on-star thing, that's not how planets form. At least it's not how most of them form, because we need a process that's way more common than that. So it must be something about the way stars form in the first place, the sort of gas clouds that they collapse from when the star forms will also form a disk of. There's some story like that. With life, we don't know. Like maybe we're looking for that sort of, yeah, it'll just happen fairly straightforwardly, and it'll still be complicated, but it happens. Or maybe, given there's lots of planets out there, maybe we're looking for an absolute weird statistical fluke, and it's just going to be really hard to work out, what's what. So, it's just a very hard problem of working out how life formed in the first place. So getting back to fine tuning, this is important. The reason this doesn't matter to fine tuning is we're just looking at some of the necessary conditions for life, and very broad, generic necessary conditions. What the sufficient conditions are, I don't know, and I don't think anyone knows.
And again, that gets back to my question. It depends on how you define life, because, even life on Earth, you talk about the conditions, life on Earth can tolerate extreme temperatures. The temperature of the oceans at they call them black smokers deep in the ocean's depths, where they think life actually began. And the temperature is some phenomenal number, like I think as high as 400 degrees Celsius. And that's also high pressures, so life can tolerate extreme high pressures and low pressures. You mentioned a few moments ago about tardigrades being able to survive the vacuum of space. pHs, we have life that forms in highly acidic environments and highly alkaline or basic conditions. So even life on Earth is very resilient and can tolerate all kinds of conditions.
Well, it's at this point I remind you that I'm an astronomer, right?
Right.
Extremes of temperature. I mean,
okay, I hear
you.
A
couple of hundred Celsius. Come on, man.
Okay, I hear you.
We've got that.
That's winter on the sun.
Yeah, the average temperature of space is minus 270 degrees Celsius, and most of the gas in our galaxy is at 6,000 degrees Celsius.
Wow.
Right, the sort of the hot ionized medium of the interstellar medium. Yeah, so I mean, extremes of pressure, like it is relative. So yes, it's much more impressive than we thought it was, but I can make a universe which never cools below 1,000,000 degrees Celsius, right? If it's short-lived, it will just live and die always above 1,000,000 degrees.
Right.
Or I could, if you make the cosmological constant too large, effectively the universe drops to very close to absolute zero, a fraction of a second after it's born. So these are important questions, but not for fine tuning.
Okay, I hear you. Now, I did want to come back to, I was clarifying what is meant by the claim of fine-tuning for life, and we clarified that a lot of that has to do with tuning a universe to be able to produce, and again, I use that term, usable stuff, which just simply means atoms, planets, and stars. So fine on that. Some people will talk about fine-tuning for life. They'll use all kinds of observations. I'll use that word. They'll use all kinds of observations like, Earth, the distance between Earth and the sun, the tilt of Earth's axis, the presence of our moon, and the presence of a Jupiter, and our position in the galaxy, our solar system in the galaxy. And personally, I don't see those as arguments for fine-tuning for life on Earth. It's more fine-tuning of life on Earth for the conditions that it finds itself in. Any thoughts from you?
Yeah, so one of the reasons why I think it's more convincing to me to go all the way to the fundamental constants, right, and look down there, is just because they are precisely where the best theories we have today. Who knows what physics does tomorrow? That's all right. It's just it's all right. But in terms of the best physics we have today, they are just ground level base assumptions, right? Just this number works, and you put it in the equations, and it explains a whole bunch of stuff. So things like the Earth's axis. So here's, the simple thing to say would be, we used to think that was fine-tuned, and then we worked out that there's a lot of different planets out there. So, there's bound to be one with just the right axis out there somewhere. And I think it's important to remember that that's just pushing it back a level. And it's important because there's a way that same move happens today. And so the question then is, all right, so as long as you make a universe with lots of stars and planets, you'll probably get the right axial tilt somewhere. Do you have to fine-tune the properties of your universe in order for it to have lots of stars and planets in it? Right, that's the next question, right? If it takes, the right axial tilt, but you'll get it if you just get enough stars and planets, the next question is, okay, is it easy to get enough stars and planets, or is that something that needs fine-tuning? And at the level we're at the moment with cosmology, right, the standard models, just fine-tuning today, yes, it does need fine-tuning to get lots of stars and planets, because, you end up with a lot of the universes, nothing sticks to each other. You don't get planets, you don't get stars.
Right.
The reason that's important is because then people make the next move, that same move again. Well, if you had a multiverse with lots of universes out there, then the right combination of fundamental constants would turn up somewhere, right? And it's important then you ask the next question, right? What do you have to do to make a multiverse, which makes lots of viable universes out there somewhere? So I think that's an important test case. I don't think it's a good case of fine-tuning, and I don't base anything on those sorts of things, other than, look, if you have an intuition that the way our solar system and the way things on Earth are set up are pretty good, as they seem to be, if that intuition works for you, then you should understand that, yes, that needs to be refined a bit as we go and look at how planets form and how life forms and how stars form and all that sort of stuff. But the same intuition will turn up when you look at the fundamental constants. And there will be a temptation to make the same move wherever you think fine-tuning is at, to make the move above it. And to remember that in the case of a multiverse, it's moved the question out beyond what we could possibly see, right? If you'd said, when we didn't know whether there were exoplanets, whether there are planets around other stars, you said, hey, maybe there's lots of stars and planets out there, and a planet with the right axial tilt, it will turn up somewhere. You could say, look, we don't have evidence of that, but we could have evidence of that. So why don't we just sort of put a bit of a hold on that and try to answer the deeper question that would turn up anyway about whether fine-tuning for planets is an interesting thing. But we've now reached the point with the multiverse, having raised that point, that we can't just wait for evidence for turn up to the multiverse, because in almost all models of the multiverse, evidence will never turn up. You'll never know whether this idea is right, because there's no way to really test it directly, at least. So that's the sort of moves that get made.
Is there any thought, not evidence, I guess, but thought that the multiverse itself would have to be fine-tuned? Like, in other words, that to come up with one fine-tuned universe, you need a multiverse. To create that multiverse, if you can call it creating it, or maybe it just always exists or something, but it also would need to be fine-tuned, or we just can't know.
There are some hints along those lines. The problem is, when we ask about the fine-tuning of the fundamental constants, everyone agrees what those are. Everyone knows what the equations are. We've tested them unbelievably extensively in our, we just have, here are the equations. Now we ask, what if I change these numbers? We don't have a standard model of the multiverse. So in some of the toy sort of proof of concept models of the multiverse, I think there is evidence of something that looks a lot like fine-tuning. So I've argued in papers, and it's in the book as well. A lot of them are based on this idea called cosmic inflation, where a very rapid expansion of the universe happens in its very earliest stages. And I think there's reasons to think that process, there's a lot about that looks like it would need fine-tuning. But because we don't have a standard model, it's very hard to answer that question. It's hard to know what to look at to try to get the answer.
Right.
So you've mentioned multiverse several times, and at least once you mentioned how it's essentially, you said something like it's something you can't test. We can't test the idea of the multiverse because anything, by definition, if it's outside of our universe, then we can't test it. So would you say then any appeals to the multiverse, that's just not a scientific explanation as often as it comes up?
So you can't directly test it in the way that, like, there's a star over there, and we look at it very closely. There's a planet going around, right? There's various ways we can do that. What we can't do is say, look, there's a universe over there. If you look very closely, it's got a different electron mass to our universe. So there's an evidence. There's evidence. We're not going to get that sort of direct evidence. What we might be able to say is that something along the lines of, okay, here's my model of how I think the multiverse works, right? Here's a map of the whole universe on an enormous scale where we are some tiny piece of it, but here's the whole lot. What you could do is say, all right, well, let's at least see whether we are typical of that multiverse. So you can imagine in your head, you get your clipboard and your pen and you go around to all the bits of the multiverse in your model. And most of them, you sort of knock on the door and no one answers because there's no one there. It's a dead universe. Like no electrons ever stuck to a nucleus, so nothing's happening there. But if you find someone who can answer your questions, ask them, like, what's the electron mass in your universe, right? And then you write that down, and then you say, well, what's the cosmological constant in your universe? And you go, okay, write that down. And once you've sampled enough people, you can then come back to our universe and say, all right, well, where are we amongst the set of everyone? And that's a way of sort of a consistency test with the multiverse. If it came back from a proposed multiverse, this is all a theory, right? If it came back in the theory that we were very weirdly off to the edge of the distribution, I suppose 99% of life forms in this multiverse idea that you've presented have an electron mass which is heavier than our electrons. That's a bit weird, a bit awkward, right? The thing that the multiverse was supposed to explain was the fundamental constant. So if it turns out that it doesn't really explain why our one is here, right? Most of them would be larger, for example. That would create a tension. It suggests that there's something about the model that doesn't quite fit our observations. The problem with that, again, just coming back around again, is because the multiverse isn't really one idea. It's sort of there's a whole boatload of ways you could make all these other universes. It just seems like it's infinitely flexible. So if your clipboard, if it comes back with the wrong answer, well, I could go change all these other universes, and none of our observations will ever get messed up like that. So the fact that you could find a multiverse that sort of ticks off all the boxes there might not be that impressive. So there'd have to be something along the lines of, like, it's also really simple, or it's very, it's all I need is the physics we already know and a bit of general relativity and a bit of something, there'd have to be some other reason why it seemed simple or something like that. But we're certainly in a region where you can understand why. There are some very senior cosmologists. So there was an article, it was 10 years ago now, but they have the same opinion now. George Ellis and Joe Silk. So George Ellis, these are two major names in cosmology. Joe Silk's at Oxford. They're both emeritus professors now, but George Ellis was Stephen Hawking's student, and they've just been major names in the field for decades. Wrote an article in Nature basically saying, look, this multiverse stuff isn't science. I mean, what do we think? What do we think we're doing? Right, we're supposed to, be grounded in observation, and that's not what can happen here. I'm a slightly more open than that. Like, it could be a convincing case for a multiverse, but it's just hard to see how it could happen. It certainly hasn't happened yet.
What about this idea we heard from another dialogue partner that said that there was a possibility they could detect a scar in the cosmic microwave background that would indicate that we collided with another universe at some point? Have you heard of that idea?
Oh, there's a few ideas along those lines. One of them is from Penrose.
Okay.
Basically, it's more of a, what if there was something before the Big Bang? What if there was a big crunch and then out we come from the Big Bang? Or there was somehow a previous universe and then we come out of the worry with that is, again, something like a Big Bang sort of erases any evidence of what came before, unless in Penrose's idea there might be some sort of, there's sort of light from the very early universe. If there were circles on that background light that were, consistently of a certain size and consistently brighter on those scales than random, that would, he thinks, be evidence of a previous universe. And It's not. I think it's the remnant of exploding black holes, something like that. You can imagine a scenario where maybe we get evidence of, universe number two, right? Over there's another universe with different electrons, or there was a universe before us. So now we've got this universe and we've got that one. So on our way to the multiverse, we've gone from one to two, which is progress. That's not nothing. But, you're not going to get that sort of direct in a way that we've now found 5,500 planets around other stars. We're not going to get that sort of evidence.
Right. Okay.
Luke, a few moments ago, you were mentioning about the data not fitting the model. You were describing some scenarios where we were talking to people in other aliens in other universes and getting observations from their universe and trying to fit it into models, and the data just not fitting the models. And that reminded me, we have come across this idea of so the one person that I'm thinking of in particular is Sabine Hassenfelder, who talks about the fact that we don't have the right model, that we've been working with the wrong model, and that's why there's so many questions we can't answer, particles that we can't find. And related to this idea would be constants that have to be tuned this way in order for the model to work, because for that model, which is incorrect, you need those particular constants. And the analogy I'm drawing, that I'd like to draw here, is that whole, the what happened hundreds of years ago, the Ptolemaic model, the geocentric model, and they created this model of the sun and the planets all revolving around Earth, and they created little contraptions where you could show the sun and the planets revolving around Earth, but they needed special gears, and sometimes they had to introduce some extra gears, extra constants, to get Mercury and Venus to go backwards at certain times. So they had the wrong model, and it took somebody coming up with the right model to suddenly put the whole story together, and it made sense. A lot of words to say, is Sabine right? Do we have the wrong model of the universe? And that's why we can't seem to answer some of these questions, and that's why we're also being led towards perhaps fine-tuning?
So I don't think anyone thinks physics is finished. So thank goodness I've still got a job.
Well, saying that the model is wrong is not saying it's finished. She is saying, I know that she has said that grants are being written to look for this particle or look for this phenomenon, and they can't. And so they try to come up with other ways to find this thing that they're looking for. And she's saying, you're not going to find it because you've got the wrong model.
Yeah, so here's the way Sabine's laid this out. This fine tuning in a general sense, not for life, just a suspiciously precise number, is in particle physics is related to an idea that they call naturalness, which is the idea that, yes, sometimes you need these free parameters, and but if you've got a number with no dimensions in it, in other words, not like, this is 10 centimeters long, that's got centimeters attached. The number I attach this depends on my units. It's, whatever, 4 inches or there's different numbers, a very small number of kilometers. If you get a dimensionless number in particle physics, if that number turns out to be roughly 1, you think, that'll be fine. That seems natural. That's all great. If that number turns out to be way different from 1, you suspect that there's something else going on, right? You've got a suspicious, again, the number is suspicious. What that's led to is, how could I change the standard model in ways that would make all the numbers more natural? What if there were other particles out there that would do this in certain ways? Now, in one sense, that led to the idea of the Higgs field, the Higgs boson, and then we found the Higgs boson. So it sort of worked at some level. This idea of, let's find a way where we could make all the bits of this theory fit together nicer. There's other ways you might be able to do it. Something called supersymmetry, which I won't even try to explain. There's some proposal for how physics might really work that would make some of these numbers a lot more natural. On the basis of that, we've done an awful lot of work with things like the Large Hadron Collider, looking for evidence for supersymmetry. And in order to make it natural, we should have sort of seen evidence by now for various reasons, but we haven't, right? So this is supposed to be the thing we were going to find after the Higgs boson at the Large Hadron Collider, and now here we are, and it's not turned up. And what Sabine is saying is that, well, look at the criteria you used. She argues that this fine-tuning / naturalness criterion is really an aesthetic criterion. It's sort of the way you think a theory would be nice and beautiful is for these numbers to, be about one. But, why, Lost in Beauty was the name of her book, her previous book. That this, all right, basically, all right, this has gone too far now. Right. We're ignoring other approaches to go down this. Oh, here's what I would love. Make me feel lovely and cozy inside if this number was this. That's Sabine's argument. So that's why there's a feeling that this sort of fine tuning. Now here comes the astrophysicist, right? That's another cosmologist saying, these things are fine tuned. That's why he has the sort of opposition to fine tuning. It's part of a bigger story, not just about life, but about how should we do physics and how should we search for new particles and all this sort of stuff. My feeling on this is that this fine tuning thing is not just an aesthetic criterion, but there are very good reasons to say, which get into technicalities about probabilities, but to say that this represents the best that we can do with the available evidence. It's not just it's nice, but it's, you have to let tension between theory and data push you somewhere. Otherwise, you're just happy with whatever theory you thought up in the first place. And, we'll just keep Ptolemy's model. Like, who cares if it doesn't quite fit? Whatever.
Yeah.
We've got to let those tensions push us somewhere. And these sort of fine-tuning criteria, naturalness criteria, are reasonable ways of reacting to tension between data and theory. The fact that it seems to be failing in this particular one way just means it, not all clues are good clues. The universe is not an easy place to work out. I don't think that's any reason to give up on the whole thing. So the way I would approach it in fine tuning is to say, yeah, we're not done with physics. The fine tuning argument, as I take it, is really taking stock of where are we? Because an awful lot of thinkers for the last 100 years or so, or more, a couple of centuries maybe, have told us that this is just any old universe. We're just accidental collocations of atoms, said Bertrand Russell. The universe has at bottom no design, no purpose. That's Richard Dawkins.
Mm-hmm.
And what fine-tuning it says is, all right, well, let's test that idea with the best physics we currently have. All right, tomorrow there might be some new physics, and that'll be great. Like, I'm not saying we stop science. I'm saying we just take stock of where we are right now. And it turns out that there's something pretty amazing going on with the electrons around here. And that's worth, thinking harder about.
Yeah, which kind of is a good segue into the maybe the final question, which is kind of the so what question. So what are the implications? Obviously, fine tuning has really entered into the popular dialogue, right? Like you hear about it a lot. Go on YouTube, you can find hundreds of videos. So the public's pretty interested in this, and I could kind of hazard a guess as to why. But that's kind of my question is, fine tuning or no fine tuning, how does that affect us, I guess, philosophically? Or does it say anything about the meaning and purpose of life? Does it say anything about whether God exists or doesn't exist? Yeah, maybe you could just comment on that.
So I'm most of the way through reading a book called The Discarded Image by C.S. Lewis.
Ah, yes.
And obviously you're familiar with it, but it's basically what did the world look like to people in the Middle Ages? And, there's a wonderful chapter on just astronomy, just the way the universe looked, that we think of ourselves as floating in empty, dark space, right? And the universe is out there. The stars are an awfully long way away. If you're in the Middle Ages, Lewis says, the darkness of space is only the shadow of Earth. The rest of it is filled with the light of the sun. And you've got to look, when you look, we think of looking out into the emptiness of space, but Lewis says you've got to try to imagine looking up at the cathedral of space. It's more like looking up at a building than just sort of looking out into a desert. And it sort of matters to your picture of how the world is put together. Not that I'm saying we go back to that picture. Well, that's not a terrible idea. But for a couple of centuries, we've been told those sorts of things like Bertrand Russell, right? That accidental collocations of atoms. The universe doesn't care about you. We're
Right.
just the third rock around some average star in the outskirts of some boring galaxy. There's just nothing, right? This is just any old universe. So I think the reason this matters is it goes, right, that affects people. It affects how you look up the night sky. I mean, Lewis points out that, Blaise Pascal saying, the infinite spaces terrify me. That's not how someone in the Middle Ages would have, right? They're not infinite empty space, right? It's the top of the cathedral, right? I mean, it might be terrifyingly high, but it's not terrifyingly empty or anything like that. It's just a different way of looking at the universe. So I think it matters if you can look around at the atoms and think, if you think that this is just some mechanistic gears churning away, the electrons go around and bounce off, and that's all that's going on around here. There's a very different way of looking at the universe to that versus, the amazing stuff I see in the natural world is made out of even more, just as amazing stuff down at the bottom. If you're flabbergasted by a hummingbird flying, then you should know that the sort of what looks like care and attention there of a master designer goes all the way down to the atoms. Like the quarks and the electrons look like the work of a master designer as well. It just changes the way you look at the universe, I think. And I think it's so seeped into our consciousness. You only realize it when you see a very different way of looking at the universes, which is why I sort of bring up Lewis, and the medievals just looked at the universe so differently. And I think that there's a very, on a visceral level, the way you deal with the night sky tells us a lot about you as a person. I think that's, how do you react to just the matter that you're made of and is around you, and how do you see it? That there's a reason to see it as remarkable stuff, as not just your average accidental thrown together stuff.
Right.
We should move towards wrapping up, but maybe there's something we have not talked about that you had wanted to, that you would like to. Anything you want to finish off with?
Oh, I should say, I've just given that sort of intuitive appeal. I think you can do an awful lot of very good work in making this argument philosophically pretty rigorous. So I was at a fine-tuning summer school, actually. It was a philosophy of religion summer school. We talked about fine-tuning for a while. There was a philosopher there, John Hawthorne. This was sort of 10 years ago, who raised a couple of, wasn't sure about this fine-tuning thing. And, he's fairly well known in this field. And over the last 10 years, I think it sort of got to him, and so for the last couple of years at least, he said, look, the fine-tuning argument is as good a philosophical argument as any philosophical argument. It's just, of course, there's things to say about it, and there's back and forth, and there's, philosophical argument, but it's good, right? It's got a lot of force. It's got intuitive force and rigorous force. You can get down into the details. So I've tried to put this together in an article of mine called A Reasonable Little Question, if people want to go find that online. But there's philosophers like John Hawthorne, Yoav Isaac's got a very good set of articles. One's called Fine-Tuning, which is very good. And another one which is about, I think, misconceptions. You can go look up their work. But this is something where, analytic philosophers getting into gear with all their logic, can make a pretty good, solid philosophical case out of this that needs very deep thought, it needs a good answer.
Okay.
Are you working on any books in the near future?
I sort of have a sort of half of one kind of written, but I'm not sure, not sure how it's going to go yet. It sort of comes back to sort of the way that we view the universe. And I think there's a worry about the way I hear other Christians talking about science. And I think that we need a better, I think there's ways that we talk about science which are just mirroring the way that atheists want us to talk about science.
Yeah.
And I think we're falling for the bait on that. I think there's a way we should talk about the universe and way we should talk about science that would help sort of break down this common sense of antagonism. But I'm still trying to work out exactly what my strategy is. I just think there's a problem there to be looked into.
I would love to see that book.
Yeah, I hope you
Seriously.
finish it. Yeah, really. Yeah. It's very much needed.
Okay, so I think we're out of time. Dr. Luke Barnes, I really appreciate you coming on, giving us your expertise. You have a whole different perspective than what we heard last week, and very different from the one we're going to hear next week. You gave us a lot to think about, and we really appreciate you giving us your time to talk about these things.
Yeah, it's been a pleasure. Thank you for having me.
Thank you very much.
All right.
Talk to you
Thanks
soon.
again.
Bye-bye.
Thanks. Bye.
Bye now. You've been listening to Recovering Evangelicals with your hosts, Luke Jansen and Scott Dyer. Send your comments and suggestions for new episodes to lukejjansen@gmail.com. Join our private discussion group on Facebook by searching for the Recovering Evangelicals podcast group. Look for the logo that you always see at your favorite podcast catcher and ask to be let in. Subscribe to lukejjansen.wordpress.com if you want to get advanced releases and group posts, or browse through our archive for a full listing of all our previous episodes. And please help the podcast by sharing with a friend and leaving a review at your favorite podcast catcher.